This presentation will be about temperature change calculations. Our lesson objectives: we will define common energy units of joules, calories, and kilocalories. We will define specific heat and molar heat capacity, and we will use specific heat and molar heat capacity in calculations. So that will include determining heat capacity from temperature changes and mass or moles, determining temperature change from mass or moles and specific heat or molar heat capacity, and finally, determining mass or moles from temperature change and specific heat or molar heat capacity. So what are these energy units? A joule is represented by the capital letter J. It is the SI combined unit of energy, kilogram meter squared per second squared. Relatively straightforward to use joules. Calories, lowercase cal, is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And I've got an asterisk here. And the reason that I have an asterisk is because this number is actually dependent on sea level and being at room temperature when you start the experiment. It's very important. The measurement of the calorie is dependent on the starting temperature of the water and the atmospheric pressure. So we now heavily favor the joule because it is a more consistent value, but we still use the calorie on nutrition labels. And you may be thinking, how? Why? What are you talking about? The kcal or kilocalorie can also be expressed as capital C calorie. Lowercase c is the amount of energy it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Capital C refers to the amount that's 1,000 of those lowercase c calories. So 1,000 calories is equal to 1 kcal, which is equal to 1 calorie. And I'm absolutely positive you don't find that confusing at all. The capital C calorie is 1,000 lowercase c calories. Yeah, no, everybody finds that confusing. It's one of those annoying historical artifacts that we just have to live with. Finally, there is a relationship between calories and joules. It is 4.184 joules in 1 calorie. Heat capacity is the amount of energy it takes to raise the temperature of a specific material. Usually comes in 2 different flavors. We have specific heat capacity, which is measured in joules per gram degree Celsius, and we have molar heat capacity, which is measured in joules per mole degree Celsius, so not much of a difference. And we have an equation that relates the two. Q, heat, is equal to M, which is either mass or moles, times C sub P, which is the heat capacity, either specific heat or molar heat, depending. That sub P refers to the phase of the material that you're working with. So solid, liquid, and gases do not have the same heat capacity. That's really important to remember. They vary depending on what phase you're in. And finally, we have delta T. So it's going to be final minus initial. Every time you use the heat capacity, remember that energy out is negative, energy in is positive. So if you're going to use your heat capacity, make sure you're using the right one. Applies to solid, liquid, or gas, whatever phase you're in, and that your sign is correct. So if you are melting something, you're adding energy, it's positive. If you are freezing something, you're taking energy away, it's going to be negative. So let's try using this in an equation. How much energy does it take to raise the temperature of 2,250 grams of wood by 470 degrees Celsius, which is around its auto-ignition temperature from room temperature, and specific heat of wood is 1.7 joules per gram degree Celsius. All right, so we have a temperature. Actually, we're going to raise the temperature by 470 degrees. So this is actually a delta T. We have a mass of stuff, and we have a heat capacity. So we're going to go ahead and just plug and chug. Right, so we've got our 2,250 grams, which we are able to use because our heat capacity is in joules per gram degree Celsius. Okay. And that is MCP, and then we need delta T, which is 470 degrees Celsius. Now, you may be sitting here and going, why am I saying that it's degrees Celsius? Why don't we put it in Kelvin? Because sometimes they do. And I'm here to tell you that if it's a temperature change, if you're taking the difference between two temperatures, it doesn't matter. The temperature change in Celsius is the same as the temperature change in Kelvin. All right, so anyway, if we plug all these suckers in and we chug through, we get 1.8 times 10 to the 6th joules, which is actually a respectable amount of energy, isn't it? Okay, so we were able to solve for energy, or Q, or heat. What was the initial temperature of water if 125 calories of heat was added to 1.00 grams of water with a capacity of 1.00 calories per gram degree Celsius and at a final temperature of 25 degrees? All right, so I like to organize information. We've got a nice laundry list of stuff like this. It tells us what our Q is. It says 125 calories of heat was added, so it's going to be positive because it was added in. And it says calories with a lowercase c, right? So this is just a normal calorie. It's not a kcal. We have mass, in this case, of 1.00 grams. Okay. And we've got a c equal to 1 calorie per gram degree Celsius. Okay, and finally we have our delta T. So what is delta T? It's our final temperature minus our initial. Right, and in our problem, we are told that the final temperature is 25. So if we go ahead and we plug all of these suckers in, 125 lowercase calories is equal to M, which is our 1.0 grams, times C, 1.00 calories per gram degree Celsius, times, and then we're going to put this in parentheses, right, because we're multiplying it by delta T, but we're breaking up our delta T into parts. And I'm going to give T final as T sub F minus 20, our T final here is 25. It's written in the problem. My bad. 25.00 degrees Celsius. Okay. And then we're going to say minus T sub I, which is for initial. And we're going to divide both sides by 1 gram and 1 calorie per gram degree Celsius. And because it's stupid easy to divide by 1, I am not going to show you how to do that thing. Just know that our calories cancel and our grams cancel, so we end up with 125 degrees Celsius is equal to 25.00 minus T sub I. Okay, now we can pull that 25 over to the other side by subtracting 25 from both sides. So we get 100, and I'm going to put a decimal to indicate this thing has 3 sig figs. And that is equal to negative T sub I. And you may be thinking, but wait a second, it doesn't make any sense. How do we get a negative number? And the answer to that is you don't really. If you take the negative of both sides, you get negative 100 degrees Celsius, which is actually a thing that you can do. If we were in the absolute scale, this would make no GD sense, but we are not. We are in the Celsius scale. So our initial temperature was negative 100 degrees Celsius, which, if we add the 273.15, gives us 173.2 Kelvin. All right, now that we've done some nice cool things, let's read the next one. Determine the molar heat capacity of metal, which was cooled by 5.4 degrees Celsius. It weighs 2.5 moles and it transferred 328 joules of heat. So that's negative 328, it's negative 5.4. We can put it into our Q equals MCAT equation. So we've got negative 328, and it is specifically in joules. That is equal to 2.500 moles. Okay, times our heat capacity, which we don't know, our C sub P, times negative 5.4. Now I've already told you that if you have a negative on both sides, you can just cancel those suckers out. We're now going to divide by 2.5 and by 5.4, and we get that our heat capacity is equal to 24.2 joules per mole, right? Because we've got moles there, degrees Celsius. That is our molar heat capacity for whatever this unknown happens to be. All right, so to summarize, joules are the SI combined unit of energy, given as kilogram meter squared per second squared. Lowercase calories, CAL, is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius, but it is both pressure and temperature dependent, which is not great. Kilocalories, otherwise known as the kcal or the capital C calories, are found on food labels, and they indicate that 1,000 calories, lowercase c, is equal to 1 kcal, which is equal to 1 uppercase C calorie. Heat capacity is the amount of energy it takes to raise the temperature of a material, and we have a relationship between calories and joules given by 1 calorie equal to 4.1844 joules. And also that Q, heat, is equal to mass or moles, M, times molar heat capacity or specific heat times delta T. Delta T is final minus initial, and always make your units match when you're using this type of equation. Hopefully you were able to follow along with that pretty well, but if you have questions, please ask.